Hey everybody, it's Ripley back again. Today we're going to talk about a little chain rule in the multivariable context. If you remember correctly, like if I had y equals sine of x squared, right? This implies that y prime is equal to, now if you remember this is sine of blah, so this would be cosine of x squared, but let's not forget our chain rule and how it gets spat a little 2x. But when we're talking about multivariable, what does that look like? If I have f of xy, which we know is equal to z, right, and I've got a function that's got x's and y's, this is easy enough, right? If I have what? 4xy plus x sine y, right? And I want to take the partials, that's easy enough, right? I go dz over dx, and I just treat x as a constant, or excuse me, y as a constant, which is exactly what we do with it. So I end up with, well, 4y, the derivative of the sum is the sum of the derivatives, and I get sine y, and then if I want to do the partial, remember I could write these as df over dx if I wanted to. It's all notational since they're equal. The partial with respect to y, let's see, what the heck would I get? I get a 4x plus, what would that be? X cos y, right? That makes sense? Because I would have sine of blah, this is just constant, sine of blah. See how you still got to think about it, it's crazy. Cos of blah, d blah, I should probably put times 1. But what happens if, let's say that instead of just an x, what if x was actually a function of t and y was just a function of t? So now I have this f of this guy. Well, let me show you something. It's so cool. I'm going to have this as z. All right, watch. It's all done with trees. The whole thing is done with trees. It's going to blow your mind how simple it is. Watch. I'm going to do z. Now, I know that there are two variables that z is used to dealing with. It's used to dealing with x, and it's used to dealing with y, but there's a problem. X's and y's both have a t in it. Now, this gets a little tricky, again, in the multivariable context. T is considered the independent, where am I? Dent variable, just like we're used to, right? And z is the dependent. So that begs the question, what are x and y? Well, x and y are the intermediate, which if you think about it from sort of the machine context, it makes sense. You stick a t into this machine that has an x and a y, that gives us an x and a y, and then that goes into z. All right, so watch how, if you get confused with these, and you can build them algebraically, you'll see how in just a sec, but if you get confused with these, you simply draw this tree again. So here's my x, here's my y, here's my t, and here's my t. So when I take a derivative, to get from here to here, I take dz over dx, and I take dz over dy. Do you agree with that? Okay? If I want to get from here to here, I go dx. I'm going to take the partial, but the partial really doesn't make any sense. I can actually write this as a full tilt boogie d because x is just a function of one variable. But I'm going to write it like a partial because it's easier to look at algebraically. All right? So this is, whoops, that's supposed to be a y and dt. So watch. dz over dt, which is what I'm looking for, I'm trying to get a derivative of this function, is simply equal to dz over dx, the partial, times, now I'm going to write it as a partial, but I could write it just as a simple d if I wanted to, and look, gone, plus dz delta, over dy times partial y over partial t. Again, there's no partial. And look what happens. dy's cancel, or partial y's cancel, and I end up with dz over dt equals dz over dt plus dz over dt, right? Now, you may say, wait a sec, isn't that 2 dz over dt? No. Remember, these are partials, right? These guys are going to be partials. So if I add up, I should do this as like part 1 and part 2. If I add the two parts together, I get this guy. Super simple, right? Now, it kind of begs the question, like, why do we have to do this intermediate stage, okay? Why do I have to go in this intermediate? Because why can't I just plug in these functions of x and y. For example, watch. Let's say that f of xy, I'm going to keep it super simple. F of xy is equal to x plus y. And x of t is equal to cosine of t plus, no, let's just leave it as cos t. And let's make y of t equal to t squared. So really, we're kind of asking the question, well, why do I have to go through all this rigmarole to get from here to here? Well, it's a little bit confusing because I am saying that z, this function, right? That's this guy right here. I just want to make sure that we're clear on the notation so we don't get screwed up. Z is actually equal to f of x of t comma y of t. So z is kind of like a function of t. Now, let's see if the derivatives work out the same way that they should. We're going to follow this guy and see what happens. So z, technically, since it's x plus y, is going to be cos t plus t squared, right? So dz over dt theoretically should be negative sine of t plus 2t. But according to this, let's check this out. I'm supposed to take dz with respect to x, right? We're going to just chug this thing out. dz with respect to x, that's the partial. So the y is a constant. So I get 1 times dx over dt. Well, dx over dt is just negative sine t, right? And then this is going to be plus, whoop, right there, plus dz with respect to y. Well, that means the x is a constant, so it just disappears when I take the derivative. This is going to be plus 1 times dy over dt, which is just 2t. Oh, we get the same thing. Now, you may say, Ripley, this is absolutely ludicrous. Why are you making us do this? Just let us stuff the dang things in. Well, it gets a little bit more complicated, but it also gets a lot more fun. So now, I'm going to say let z equal f of x, y. Now, again, when we're just composing single variable functions into this guy, that x of t and that y of t, it's a no-brainer, right? You just stuff it in there and take a derivative. But what happens where x is equal to its own function, right? So let's call it of two variables. Let's call it g of st, and y is equal to h of st. Oh, good God. Now what happens? Well, now we're expanding sort of geometrically, aren't we? Now, let's just look at what the tree looks like, all right? So I got z. Now what happens? Well, I pop out here and I get an x and a y, just like before. But the problem is that x pops over and gets me an s and a t, as does the y. You with me? All right, so let's see how we get from here to wherever we need to get. I'm going to take a partial with respect to x, and then I'm going to get from here to here. I'm ignoring this. Don't get freaked out about that. I'm going to take the partial to get from here to here. So I got dx over ds, and then I'm going to have partial x over dt, right? You with me? And then from here to here is the partial y over ds and the partial y over dt. Now, if I want, notice I'm going to get partials of z that deal with the s and the t differently. So I'm going to have two separate partial derivatives. Not as intuitive as just plug it in, right? If I want dz over ds, let's put that as this guy. Well, what happens? I need to pick up all the paths that get me from z to s. Well, that's going to be this path, and that's going to be this path. So what's that look like? Well, it's dz partial, right, times s plus, I missed my z over y, didn't I? You guys got to yell at me, man. I'm slipping. No, I'm not. Never been better. I got this guy. And now I have my partial with respect to s. If I want my partial with respect to t, remember the whole reason we're doing this is because we have introduced two variables inside of the two variables, right? So dz over dt, now I grab the other path. I'm going to grab anything that gets me to a t, and it's going to be those two, right? Get back to black, and I'm going to have z partial with respect to x times x over dt plus partial with respect to y times partial of y over t. That's pretty cool. Now, if you think about this, this could get out of hand, right? I could have multivariables in here. I mean, look at how ugly this would get, but it's so sweet because it just generalizes it. Let's say that that z is equal to f of x, y, and z, and x is equal to g of a, b, and c, and y is equal to h of a, b, and c, and z is equal to, what should I call this? Let's go L of a, b, and c, right? Well, we don't panic. We can generalize this thing out as far as we want, but realize this. How many partials are we going to take? I'm going to need a partial with respect to whatever my independent variables are. So however many independent variables I have, that's how many partials I'm going to need at the end of the day. Remember, these guys are intermediate, these guys are independent, and this guy is dependent. So I'm going to need one of these, I'm going to need one of these, and I'm not going to make you go through this with me. I'm just going to show you the tree because it's pretty cool, and I like it. One of these. So here's z, right? And then I'm going to have three of these bad boys coming off, x, y, z, and then I'm going to have three of these bad boys coming off, a, b, c, a, b, c, a, b, and c. So if I want dz over dA, whoops, yeah, I want that, right? Then I'm going to have to follow, I'm going to have to add three paths. That guy, wait, oh wow, did I really go z as a function of z? Blah, crap. Oh, man, maybe I am slipping. I haven't eaten lunch yet, so let's change that to an alpha, because I'm a moron. You see, you let these things slide and then see what happens. Let's call this alpha. So that would be an alpha, right? And then wham, and I follow those paths. So instead of adding two terms like I did over here, we'd be adding three terms, which is awesome. Now, let's talk about second derivatives. Okay, so I'm gonna deal with it in this context, but I'm gonna give myself some space because that page is just ugly. All right, second, whoa, wowza, try that again. Second partials using chain rule. So second partials, I love these. They're so much fun. Using, I think you'll like them. They're fun to draw the trees anyway. Using chain rule. I told you chain rule was everywhere, baby. You can't escape it. One thing that I do want to mention about second order partials is that if you're playing around with z equals f of x, y, and we're taking second order partials, then we got to make sure that we have continuous second order partials throughout. In other words, all partials are their derivatives are continuous. All right, now remember, when we first learn about partial derivatives, now in the context of chain rule, the chain rule still applies, but we need to figure out which partial we're playing ball with, right? If I'm talking about, remember, this is my partial derivative with respect to x, but this can, if I take a second derivative of this guy is going to be referred to as d2z over dx squared, right? This, excuse me, is take the first partial of z with respect to y, and then the second partial. So we would write this as d2z over dy squared. However, just like we talked about before, every one of these derivatives, if I take a derivative using a partial derivative, then I potentially might have to use chain rule, right? So even this guy, if I've got xy, then what's this thing going to look like? Well, it's going to be d2z over, and this is going to be dx dy, but all of these can have different chain rules involved in them. So you want to be really careful with that. I'm going to give you an extra credit problem out of this section that's pretty beefy. It's got an example that goes along with it, and I want you to be able to try and play with that thing because, man, it'll twist your head up if you're not careful. That's supposed to be and dz. All right, so, or excuse me, x. So the moral of the story with using chain rule with seconds is to really pay attention to your notation. I prefer the standard issue sort of Leibniz notation that we've used in the past. This gets a little confusing to me. It's like, wait, what do I start with? Do I start with the y or do I start with the x? Well, it's in order, which isn't that bad, but you do want to be fluent in both of them. Okay, anyway, enough of chain rule. Let's talk about implicit differentiation in multivariable calculus. All right, so now we're talking about implicit differentiation. Implicit diff. Now, let's review, okay? Remember where implicit differentiation came about. Like if we had x squared plus 3xy plus y squared equaled 5. Remember this guy? Now this is an ellipse on an oblique axis, but we ran into trouble because we couldn't solve for y, so we didn't have a function of y. This thing could not be written as f of x equals y. I can't do that. So let's say similarly that we had, I don't know, x squared y plus 2yx plus xyz equal 3. Now, I'm an idiot to try and do this, but I just want to make sure. Let's go. I wanted x squared yz plus xyz squared. Now, I'm not going to even try and figure out what this thing looks like. It frightens me. However, do you see what we have here? I can no longer solve for z for the same reason that I couldn't solve for y up here, right? So if I'm looking for things like, remember up here I was looking for tangent lines because I'm not going to try and figure out what this thing would look like, but let's say it looks like that. And if I'm trying to figure out lines tangent, I needed a little bit more information, but that wasn't a big deal. But it was super simple, right? I just went like this, and I cheated, and I threw in a little d over dx, and every time I differentiated y as though it was an x, I left a footnote. Well, it's a little more complicated here because now instead of looking for lines tangent to this surface, now I'm looking for planes tangent. And remember with planes, what I need is if z equals f of xy, then I'm going to need partials. I'm going to need dz's over dx's, and I'm going to need dz's over dy's to build the equation of the tangent line. That's what the equation has. Remember, I'm not going to insult you by writing that thing over again. So let's think about it. For example, if I had x squared plus y squared plus z squared, now we can get our brains wrapped around something, right? Now in this case, I could solve for z, but I'd have that same problem that I had with circles if I had the top half of a sphere of radius 2 and the bottom half of a sphere of radius 2, right? And then I'd have to deal with it. So it sure would be nice to be able to come up with a way to take partials as it sits in here. All right, there is. Now it's going to take a little bit of faith though. There's something called the implicit function theorem. Function theorem. Okay? We are not going to try and prove this in here. This is definitely an analysis topic. It would take a week for us to get into the nitty-gritty of the proof of this. Now, let me tell you what it says. It says, let's say we have a capital F. All right? Now, we're calling this thing a function. All right? And it's going to be x, y, and then it's going to be a z. But another way to write this, and this is where notation can get out of hand, is x, y, and then little f of xy. All right? Now, in the implicit function theorem, it says this. It says that this guy has to equal 0. It also says that the partial with respect to z of x, y, z cannot equal 0. All right? That's what it says. Now, bearing in mind that what I'm about to do is to exclusively produce a partial with respect to x. I'm going to use the chain rule really quickly. All right? If I've got f of x, y, and z, and I want to differentiate this thing to produce a dz over dx. Now your spidey sense is probably tingling a bit because of what we did with implicit differentiation. But now we're going to use partials instead of outright implicit differentiation. So watch what happens. What I'm going to get is I'm going to get a partial of f with respect to x times, now chain rule says I got to spit out the partial of x with respect to x plus the partial of f with respect to y times, with respect to y, times the partial of y with respect to x, right? We do a partial, we got to do this chain rule, true? All right, this is going to be plus the partial of f with respect to z times the partial of z with respect to x. Now we have taken the partials of all of the independent variables and we've used chain rule independently with respect to x because I'm dealing with a delta x, right? Basically, remember, this guy is just d over dx of f, and f is this. Now, notice a couple of things. First things first, what is this partial of x with respect to x? Well, it's 1. What is the partial of y with respect to x? If I take this of y, what do I get? I get 0. This term drops out. You with me? And I know that this guy's going to equal 0 because if I differentiate this side and this side, just like we differentiated, ooh, I missed my parenthesis over here, didn't I? Both sides of this equation, then I end up with this. Now, why is this so important? Well, because of this guy right here. This right here. It spat out the partial that I needed. So in a puff of algebra, I can easily show that dz over dx, which is what I need, that partial over dx, is equal to the partial of f, but negative, because I'm going to send it over to the opposite side of the equation, right, with respect to x, divided by the partial of f with respect to z. Awesome, right? Now, if I do exactly the same process, but instead of differentiating with respect to x, I do it with respect to y, well, I'll get a df over dy, df over dy, df over dy, df over dz. This guy will turn into 0, this guy will turn into 1, and in a puff of algebra, I will get negative partial with respect to y over partial with respect to z. And I have everything I need because of the equation of the tangent plane. Now, I realize this is a lot less intuitive than this guy was, right? This was pretty intuitive. Everything fell out. Poof, you ended up with the dy over dx. Well, this one, you're just going to have to memorize these formulas or put them on your formula sheet. All right, ladies and gentlemen, that was a long section. I hope you got some information out. We're going to have a great time with some problems. You get a little extra credit as well. So I will see you in class tomorrow. Have a great